So yeah, I'm Johan Medrano. I'm a postdoc at the Wellcome Center for Human Neuroimaging. Um, and I'm going to talk about reverse engineering artificial life under the free energy principle. But first I will thank the organizer of this workshop for putting everything together and inviting me in the panel. Can I move my slides? Yes. So I'm going to start with an idea from Helmholtz in the 19th century, which is the brain continuously infers the causes of our sensation, which means that the brain or like adaptive behavior arises from like some kind of probabilistic inference going on. And the kind of question I'm interested in is how can we recover the probabilistic models that drive these inference processes? And I'm going to do this under the free energy principle. So I'm going to first introduce the free energy principle and first like two theoretical devices, which are Bayesian inference and Markov blankets, before staging the free energy principle. So Bayesian inference really reflects this idea of refining some beliefs given some observations. So you've got some belief about, for instance, the causes of your sensorium, and then you've got some mapping from your belief into your sensorium. You observe something under your data likelihood, and you can refine your beliefs from prior beliefs in posterior beliefs. In general, this is Bayesian inference, and in general, it's not tractable just because your model is too complicated or you're constrained. Your model is not directly tractable. So the true posterior beliefs might be intractable. And so a very naive idea that you can try to do is to approximate your posterior belief by introducing some kind of distribution that you know from a class of model that you know, or with like a physical implementation that you know. And then you can try to minimize the KL divergence, or like the distance between the true posterior beliefs and the approximate posterior beliefs. So this is like very machine learning engineer approach to inference. And so you could do that through gradient descent. The problem is that this distance is actually intractable, so you cannot compute it. However, if you take this scale divergence, or like this distance between distribution, and subtract the log probability of your data, then you obtain something which is the quantity F here, which is the free energy. And you can then optimize the parameters of your approximate distribution to do gradient descent on the free energy, and the gradient. So this quantity is tractable, and the gradient will actually be proportional or equal to the gradient of the KL divergence. So you can actually, so the F here is called the variational free energy. And basically, if you've got a particular constraint on the model family, or you know which kind of, so in machine learning, for instance, you will take your approximate posterior to be a Gaussian. If you want to find the best approximate posterior under like a particular family, you can just minimize using gradient descent the free energy. The second thing I'm going to talk about is the concept of a Markov blanket, which is simply the collection of random variables that is sufficient to completely determine a target random variable. So if you've got like a probabilistic graphical model with nodes depicting random variable and edges being depicting the conditional dependence between variable, if you select one node, for instance, C here, the Markov blanket of C will be all of the nodes, so B1, B2, B3, that are like sufficient to completely determine C. And what this means is just that if I want to compute C and I've observed B1, B2, B3, then observing A will not provide any information on C. Now, from these two devices, we can introduce the free energy principle, which is like a normative account of adaptive behavior. And for this, we will start with imagining that we've got a system that has like a large number of variables that are ruled by some physical description, so like a differential equation with some noise, for instance. And the first thing that we will do is to try to separate this variable and to kind of partition the state space. So for instance, if we think of a cell of a bird, there will be some states that will be like internal and some states that won't be. So the first thing is to pick some states as internal, and then to look at the Markov blanket of this state. So all of the states that will completely determine the internal states. We can label all of the other one as external states, and then we will just find the states that are influencing the external state, but not influenced by the external states. So this one will be called active states, and then the remaining one will be sensory states. No, so this is the kind of structure to which we can then apply the free energy principle. And so the free energy principle will have two main components. The first one is that the internal state are assumed to parameterize an approximate posterior on the external states. So it's really this idea, like going back to Helmholtz, that the internal states are trying to infer the cause of their sensorium. And what it means in probabilistic terms is that there is some kind of approximate density that is parameterized by mu, the internal state, and that is trying to approximate the distribution of the external state given the sensorium. The second thing is that so this model is updated to approximate as best as possible the actual posterior, the true posterior. And this is done by having a gradient flow down the free energy. So the internal state are flowing down the free energy, which means this is like exactly the model estimation that I was showing in variational Bayesian inference before. And the active state are also flowing down the free energy, which means both making the model more accurate, but also like manipulating the sensorium such as like it's more predictable. So now if we like look at the bird video that I was showing before, and we try to like understand what happens under the free energy principle and under like its process theory, the active inference theory. So first there will be, for instance, a change in the external force, for instance, a change in the wind flow that will be a change in the external state that will cause a change in the somatosensory receptor, so change in the sensory states. But then the internal states are trying to predict the external state. And that means that there will be like a likelihood of the sensory states given the internal state, and that can create like a prediction error that will be like compensated. So that will be like an update of the internal model by gradient descent on the free energy. And then an update of the muscle configuration by gradient descent of the free energy with respect to the active state. So that will update the kind of force that is applied on the bird by just changing the bird configuration. And this will be repeated until there is no error in the predicted sensory state. So it's really trying to, here inference is really, the inference of the agent and its environment is really trying to put itself into a predictable sensory state. So the free energy principle has been used to engineer adaptive systems. And like the free energy principle is a principle like the principle of least action. And as such, the free energy plays kind of the role of a Lagrangian or Hamiltonian in classical mechanics. So it's like a statistical, it's a static quantity that can then be used to derive the equation of motion. So the particularity is like this quantity, you will describe it through a generative model. Here, that will be, for instance, prior beliefs. So the idea that the velocity of the bird's head is a Gaussian centered around 0, and then the likelihood of sensory data given the configuration of the internal states. So like a mapping towards the sensorium. And then you can do like you would do with the Euler-Lagrange equations to derive the equation of classical mechanics. You just run the active inference process. And the very nice thing is that under different models, you can obtain PID control, optimal control, you can obtain Kalman filtering, and like very like useful engineering algorithm. And so the main question I'm interested in is like, for a given system, can we do the way back? Can we reverse engineer what is the generative model there just by looking at the dynamics? And the focus of this work is just to look at what tools are actually available and what tools need to be developed. So for this, I looked at a system of chemical autonomous agents. So this one has been introduced by Stuart Bartlett and David Luop in the Provenance of Life paper. And it's a chemical reaction network, which consists in a dissipative structure with autocatalysis, homeostasis, and associative learning. So it's constructed from a base network where there is a compound B with logistic growth. a toxin T, which quickly degrades B, then a stimulus S that arrives before the bolus of T, then an antidote N that degrades T quickly and B slowly, and finally a defense network. So that's the thing we can kind of play with. That is catalyzed by B. So if there is no B, there is no defense. And it produces N to protect B, so to protect the compounds from the toxin. So it's really something that will generate antidote to protect the main compound from the toxin. So the author of the original paper investigated 3 different networks. The first one is the direct network. It generates the antidote from the toxin. The second one is the preemptive network. It generates the antidote from the stimulus. And the third one is the associative network. It's a bit more smart. It generates first like a short-term memory M from the stimulus. When the short-term memory is in presence of the toxin, it generates the long-term memory. And when the long-term memory is in presence of the stimulus again, it generates the antidote. So this network, you can apply reaction kinetics, and you can just stimulate in 0D well-stilled solution with a bolus amplitude described by the sum of the 3 components of the Lorentz system, which is like the curve here in U. Then orange would be the bolus delivered, the toxin bolus, and V would be the delivery of the stimulus. If I look at the direct and preemptive network, so we can see that the blue curve, which denotes the compound B, is quickly collapsing to 0 in concentration, which means that the compound B is just destroyed by the toxin. There is no response, and there is no survival of the chemical autonomous agents. However, in the associative network, the compound is actually preserved for time, and this is through generating like adequate quantity of antidote to counteract the presence of the toxin. So that's the kind of phenomena that we want to try to analyze, because it's an adaptive phenomena. So we want to look at this under the free energy principle. And so towards recovering the generative model under the free energy principle, I will follow like a few steps. First, I will try to partition the state space, then uncover the synchronization and active manifold. So basically, this is just something that gives the internal state as a function of the external state and the active state as a function of the external state. And it's like a structure that kind of arises from the fact of specifying the generative model and using the gradient descent on free energy to keep the dynamics. Then from this, I will look at the synchronization map, which kind of gives a mapping between the internal state and the external state without reference to the blanket state. And finally, I will look at the internal probabilistic model that is recovered from the synchronization map. So to partition the states, I will use the Jacobian of the reaction kinetics to identify the directed coupling between the concentration. So basically, you would have an arrow in a graph between compound I and G if I is appearing in the flow for J. So if I look at the direct and preemptive network, so these are the network that are uncovered by this method. There is no way of there is no meaningful partition that can be found. So you cannot find the partition to which we want to apply the free energy principle, and that can be confirmed quite easily just by applying the definition of a Markov blanket. However, if we look at the associative network, we see this kind of structure that is there by taking the internal state to be the long-term memory L and the short-term memory M. We see that the external state will be the amplitude of the bolus and like the stimulus function. And then the blanket states will be all of the remaining states, with the active states being the antidote, which kind of makes sense, and the compound, and the sensory state being the actual concentration of the toxin and the actual concentration of the stimulus. So now that we've got this kind of separation to which we can apply the free energy principle, we can look at how the internal state and the active state are reacting or like connecting towards the external states. And so the nice thing with the free energy principle is that under some assumption, the active states will collapse exponentially quickly onto an active manifold, and the internal states will collapse exponentially quickly into a synchronization manifold. And so to kind of find these structures, we can plot the concentration of the bolus concentration, so the external state, as a function of the active states for the active manifold. So this is what it gives. So we can see like the structure of the Lorentz attractor that is kind of reproduced in this space. And the second thing is we can do the same kind of plot, but as a function of the internal state. And once again, we see some kind of structure. And the very interesting thing here is that the concentration of L, so the internal state, is scaling with the concentration of the amplitude, of the bolus amplitude. So we can use this and try to understand like so the hint there is that the concentration of L is mimicking the bolus amplitude. We can recover this just by looking at the synchronization map. So under like some assumptions, there is a map that maps from the most likely internal state to the most likely external state without reference to the blanket state. And to find this synchronization map, we can just, so heuristically, we would just take the concentration of L and the concentration of the bolus amplitude. We're not so interested in M for here, but and do the linear regression of one against the other. So doing this, we can actually regress some kind of linear map. So it would be like a linear approximation to a partial representation of the synchronization manifold. And then once we've got this map that projects, that calculates the external state from the internal state, then we can look at this as encoding how the mode of the internal distribution is projected onto the external distribution. And we can try to use that to reconstruct the external state from the internal state. So this is the blue curve that is here. And the orange curve is the actual amplitude of the bolus. So we can say that so there is between the stimulus, there is like a quick decay of the predicted external states, and it comes close to the actual realization of the external state. So to confirm this a bit more, I looked at the distribution over like a interstimulus interval. So really like on the peristimulus time, look at how this is moving through time. So just averaging or like computing the density plot over all of these stimuli. And we see that when there is the stimuli, so it's like the peristimulus time 0, there is a disruption of the encoded distribution. So this is the distribution of the external state as recovered from the internal state. So just by doing a linear mapping from L onto the bolus amplitude. And this is the actual distribution of the bolus amplitude. And we can say that there is the disruption and then it like kind of revert back to the actual distribution. So we are really like in the presence of this kind of mechanism that Helmut is talking about trying to, like an agent trying to infer the cause of its sensorium. And we can confirm that by just looking at the KL divergence between the two distributions, and eventually we can say that it's disrupted at the onset of the stimulus and then it's regressed back to 0. Another nice thing that we can do is just because of the existence of this manifold, we can just solve the unmanifold solution for L and then takes the temporal expectation. So that makes sense just by considering the fact that the long-term memory has very slow reaction rate, so it's catalyzed really slowly, which means it's kind of averaging out all of the fluctuation of all of the other compounds, which means that this L is kind of reflecting some kind of expectation, and it's capturing the covariance between the toxin and the stimulus, which themselves are closely mapped to the toxin delivery and the stimulus delivery, or like the two boluses. Which means that if there is like a strong overlap between the two, then L will be like quite strong, and then the L is itself modulating the generation of the the antidote. So we can see here that the antidote is actually proportional to the stimulus times the covariance of the two. And yeah, the nice thing here is that the covariance between these two states can be seen as a form of Avian learning. It's really like the same functional form. And just like to wrap up and to conclude, we use the free energy principle to find a meaningful partition of states, which are just like based on the directed influence between the different quantities in the system. Then we identify the synchronization and active manifolds when covered like an approximate posterior, and we recovered separately the rules for Avian learning in the system. And some like limitation and extension. So things that are I would be really interested in would be, can we determine which external dynamics the system can adapt to? So for instance, here we say that the system can control its distribution back to the posterior. Is there things that I can put in as stimulus that will just, that the system cannot adapt to? Probably yes. What are the rules for this? Then can we construct an explicit approximate model of the agent's approximate posterior? So here, like there is like a very complicated process to kind of go to the approximate posterior. Can we just construct a model, a probabilistic model of this, and just fit the agent dynamics with this approximate model? So we would have an approximate model of the agent's approximate posterior. And the third thing would be, can we determine an admissible range of parameters, for instance, here the reaction rate, that lead or not to adaptive behavior? So can we like kind of find the boundaries that on the parameter space that allow the agents to kind of adapt, and like how does this connect to information processing? And I'm just going to thank people from UCL, Peter and Carl, and like and Lance and other people from my PhD, and also thank you for your attention. And I would be happy to take any question.
Yes, thank you.